I'd now like to talk about quantum number sets and allowed values for quantum numbers. First of all, let me describe what a quantum number set actually is. And if we were to use something fairly simple, let's say we wanted to locate a certain electron, and let's say we just wanted to locate this particular electron. Then what we could see is that it's in the 2p, and I'll just isolate it. It's in the 2p, and it's in the second orbital of 2p, and you can see that it's sticking downwards. And what this would indicate would be, just for this particular electron, that I could have this 4 number set that would actually let me know where that electron is. So n equals 2, and that would describe the Bohr orbit that it's located in, and we've already discussed that. Then you've got another quantity, L, and in this case L equals 1, which defines, n equals 2 is that, L equals 1 defines this as being the p orbital. Then we've got m sub L, called the orbital momentum quantum number, and this will allow us to tell us that it's in this middle orbital of the p set. And then we've got the last one, which is m sub s, and this one's negative 1/2, and what this tells us is that it's pointing downwards. So every electron in every orbital set has, or in every orbital has, a certain set of 4 quantum numbers that identifies where it is in relation to every other electron, and this is an indication of its energy and basically its location amongst the other orbitals. Alright, so let's look at where these quantum numbers come from and the allowed values for these quantum numbers. Alright, so you're familiar with the standard Bohr orbit configuration. We've got a nucleus here and we've got 4 Bohr orbits. Now each of these Bohr orbits is split up into separate orbitals, just like I was showing you earlier with neon. We noticed that neon was split up into 1s, and then for n equals 2 that was 2p and 2s. Now if we keep on going, we've got n equals 3 and we've got n equals 4 as well. Now what we're going to do here is define the allowed values for each of these sets of numbers. Now for the n values, we can have n can be allowed, or I will let's put it right allowed here, allowed for n. N can equal 1, 2, 3, etc., etc. N can never equal 0. So n is going to be the approximate Bohr orbit. So it'll tell us, give us a very rough idea about where an electron might be. Now let's look at allowed values for L. Now L can equal any value from 0 up to n minus 1. So what's happening here is that the value of L is going to depend on the value of n. Now what I mean by that is this: if I've got a value of, say, n equals 3, that means my values for L can equal 0, 1, or 2. Now what do these L values mean? Well, for the L values, L equals 0 indicates an s orbital. L equals 1 indicates a p orbital. L equals 2 indicates a d orbital, and L equals 3 indicates an f orbital. So these numbers represent codes for the different orbitals. So you can see now we're able to sort of zero in on the location of an electron. So if n equals 3 and L equals 1, what we're talking about is 3, and we're talking about the p orbital. So we know the electron would be somewhere in this business, somewhere around here in one of these trees. So let's see how we can figure out where those where the electron would be within those 3. Get a little more space here. Alright, so and the next one we talk about is m sub L, which is the orbital quantum number, or the angular momentum quantum number, and this can have a value of L, negative L, to 0 to plus L. So if L happens to equal 1, as we were talking about, then the allowed values, well, so let's see, so n equals 3, and we say L equals 1, then m sub L would be have an allowed value from negative 1, 0, or 1. So it would be negative 1 through to 1, which is 3 values, which happens to be the number of orbitals we could expect for a p sublevel. And if I was wanting to point out this one, this would be m sub L is equal to 0. So this would be negative 1, this would be 0, and this would be 1. And that's how we could manage to figure out where an electron was in this particular sublevel. So each of these levels here is called a sublevel. Alright, the last one is m sub s, or the spin quantum number, and it can be negative a half or plus a half. And basically all this is saying is the electron is either up or down. So let's say the electron was pointing up, then what I would say is m sub s equals plus 1/2. Now each of these orbitals can contain a possible 2 electrons, but if there's 2 electrons in the orbital, one has to be up and one has to be down. Alright, so these are all the different allowed values, and as I said, we can use this to locate an electron. So if I want to locate this particular electron, then the four number set I would use would be n equals 2, L equals 1 because it's in the p orbital. If it was 0 to be s, 2 is d, 3 is f. And we've got 1, 2, 3, so m sub L can be negative 1, 0, or 1, and it's in the 0, so m sub L equals 0, and since it's pointing down, m sub s equals negative 1/2. Alright, let's go back to the diagram I've got over here. Alright, what I want to do is point out the different numbers of allowed values for the different orbitals where n equals a certain number. So let's say n equals 4. Now what I want to point out here is that while I've got n equals 4 drawn out all separately, the 4s actually appears below the 3d when we draw our orbital diagrams. So don't let that confuse you for now. I'm just trying to show you something as regards these values and their allowed values. So let's let n equals 4. Now if n equals 4, that means the values allowed for L would be 0, 1, 2, or 3. What that means is we can have an S, we can have a P, we can have a D, and we can have an F. So that means that if we've got a value of n equals 4, we can have 4S, we can have 4P, we can have 4D, we can have 4F. Now if we let L equals 3, which is an F, then we can figure out how many of these lines we're allowed to have. And we're allowed to have as many as what we've got here, and negative L to plus L. So it would be negative 3 to plus 3. And you'll see that that's how we get that an F sublevel would have 7 orbitals, because we can go from negative 3 to plus 3. And then of course we can have the electrons in here, and they can be up or down, and they could be in any one of these particular locations. Alright, so let me show you the other implication we can have here for allowed values. So that's for when n equals 4. What about when n equals, say 2? If n equals 2, the allowed values for L would be 0 or 1. What that means is we can have 2s, or we can have 2p, and that's it. Now we can't have 2d because the value for L can't reach 2. That would indicate a 2d if that were possible. Now the reason for that is because you can see as we as we go out, the areas around the nucleus get larger and larger. And n equals 1 can only fit one orbital type, and that's 1s because it's so close to the nucleus. N equals 2 can fit s and p, but it can't fit d because it's too close into the nucleus. 3 can fit 3s, 3p, and 3d. And 4 can fit all of these because it's far enough out from the nucleus to have have enough room for all of these different orbital types. Remember, all of these orbitals represent spaces where we can find electrons, and we need the space in order to accommodate all those electrons if we're going to be considering things that are close in or far out from the nucleus. Alright, so that's our introduction to allowed values of quantum numbers.